So, chapter 20 is on electricity. Now, when we talk electricity, we can split it up into two separate categories. There's current, which is circuits and such, and we'll start talking about that later this week. But the first portion is electrostatics, meaning how do electric charges interact with each other when they're not flowing in a wire. So, before we can really delve into the good parts of electrostatics, we need to make sure we understand what the basic pieces for electricity are. What are the two fundamental charge carriers? Do we know? What are positive and negative? Electrons and protons. Protons and electrons. Statics, which I totally said earlier. All right. So we talked about protons and electrons already this year when we talked about the atom. What do you remember about protons and electrons? All right, positive. What else? All right, in the nucleus. Keep going. They're positive and in the nucleus. Jack, what do you have? They're positive? Okay. All right. Maybe we should jump to electrons. What do we remember about them? Okay, good. All right, and in the electron cloud. What else? Okay. Often blue in pictures. I don't know that I'm going to write that, but you're not wrong. That's definitely something we saw frequently. What did you say, Eva? Oh, okay. Other things that we remember about protons or electrons. Which one? Okay. So when we talked about protons and neutrons, we said they were 1 AMU, atomic mass unit. How big were electrons? 0, so basically 0 mass. Okay, what else do we remember? What was the purpose of a proton? What could it tell us? Okay, so determine atomic number. Well, what did electrons determine? Okay, so these determine charge. What else? How about protons? Did they tell us anything else? Also charge. Okay. All right, so we could also say that electrons determined reactivity. Okay, but you guys got the big idea that the electrons and protons are the basic charge carriers. Now, when we talked about them, we said that the protons were what amount of charge? 1. We said it was positive 1. What unit? That's because we didn't say a unit, which is really weird given that every other measurement and every other quantity we've had this year has had a unit. Whether we were talking about distance in meters, time in seconds, frequency in hertz, everything has had a unit except for the charge of protons and electrons. They've just been positive 1 or negative 1. Well, when we talk about charge in physics, we actually need a unit to measure this in. And the unit we use is coulombs. That thing right there, coulombs. Sure, it's a guy's name. That's a person's last name. Okay? So, to give you a little bit of perspective as to how big a coulomb is. Well, protons and electrons are incredibly small. A proton has a charge of 1.6 times 10 to the negative 19th coulombs. And an electron is just the opposite, negative 1.6 times 10 to the negative 19th coulombs. No idea. So it takes billions and billions and billions and billions of electrons or protons in order to get a charge of 1 coulomb. So that's a lot, and it really doesn't leave us with a good understanding of how much is a coulomb of charge. However, if we start talking about something like a lightning bolt, did anybody happen to know or want to take a guess as to how many coulombs of charge a lightning bolt is? So I got 3, and I got 1,000, 5, 4 million, a billion, and 6. So those of you who are in the single digits aren't far off. Okay, your standard lightning bolt, and I'm talking earth to sky lightning bolt, or sky to earth, either way, is between 10 and 20 coulombs. So a single coulomb is an incredibly dangerous amount of charge. Okay? It's not far off from being enough charge to jump up into the sky or lance down from the sky to hit Earth. Okay? In terms of static shocks that you and I would experience, like if we walk across carpet and touch a doorknob, static shocks are usually 1/1,000,000th of that size. Static shocks less than 10 to the negative 6 coulombs. So they're very small by comparison, though actually measurable and feelable. Okay? Now, we talked a little bit about what are the charge carriers, how is charge measured. Next up, I want someone to give me a second grader's understanding of how positive and negative charge interact with each other. What about opposites? Say again? Okay, so we know opposite charges attract. And what else could a second grader tell me about charge? We'll get to that one in a minute. What's the other piece that a second grader could tell me about charge? Ethan, what's the other half? Or Jack, that works too. Okay, so let's pick a word rather than make up one. I get what you're saying. Now use a real word. I like repel. All right. So opposite charges attract, like charges repel. Something that is very basic and that we've heard for years, right? Okay, now Kendall had gotten to the idea that if you take a balloon and you rub it against your hair, you can get static electricity. Well, that actually leads into our next piece, which is how do you move charge? So charge transfer. And the method she described is charge transfer through friction, which we will also call the triboelectric effect. Now, if you remember from November, we'd indicated that different atoms, different types of elements, have different attractions for electrons. Well, we're going to basically say the same thing again. Different materials have different attractions for electrons. And when two materials with different attractions are rubbed together, one gives electrons to the other. In that case, yes. Two materials. Get to that in a sec. Have different attractions for electrons. For electrons, the one object will always give electrons to the other and they're rubbed together. One will always give electrons to the other. When rubbed together. Yep. All right, so demonstrating the triangle. What else I've got up here? Rabbit fur and a plastic rod. So you take the plastic rod and it's rabbit fur. Now, because they have different attractions for electrons, the fur is one of the most positive things we can find, and the plastic is one of the most negative. And the rod is negatively charged, so the rabbit is positive. You could really have that's okay. So, again, it's not falling down. Pretty sure. I would hope so. Okay, so here is asked which one's positive, which one's negative. Really, the triangle effect is a series, and you can just list any of different materials. And once you test the current materials, this will always be negative when rubbed against the side. It's going to be every time. How do you know? Well, you test it against something that has a charge that you do know what it is. So, that's what I'm trying to do. That one you know. Like how do you do the first one? You'll have to get it experimentally in some way. You have to establish through some known experiment. What if that experiment and the whole everything else is wrong? The 100% of everything is backwards, and electrons and protons are negative. And you know how much that matters? A lot. Then why are we? Because we need to have a designation for the negative charges. What matters is that opposite charge. If someone's positive or negative, if you want to know the left charges and charges, it would be the same thing. Well, I wouldn't care. What matters is their opposites. And actually, we use positive to designate opposites. There's nothing about them innately that means this has to be positive. In fact, Benjamin Franklin thought that it was the positive charges that moved electricity movers. As we'll learn later this week, he was wrong. And we've been working with him for 3 years. Yeah, see, what no. We tested it repeatedly. So, going back to the triboelectric effect, guys, let's talk about some of the demos. They're way fuller. Again, triboelectric effect. You can rub the plastic rod against the rabbit for it gives up electrons. We can use a microscope to see the electrons. And become positive. The next one on your list. Remember the reading from Friday. What was another one on your list? Remember back to reading Friday. What was another one of the methods of charge transfer on your list? Next shot. Electric transfer. Still searching in the dark. Electronic transfer. Light. Okay. Okay, check your notes. Well, there's 3 methods of charge. Check your notes. Right. Yep. Oh, we're busy. Yeah. And then the other 2 classes. Yeah. So, class 3, you guys. Hey. And I need to talk not further. Go ahead, Jim. Say again? No. All right. So, next type of charge transfer we're talking about is contact. So, From here, I've got electrons on the plastic. Charge transfer through contact occurs whenever two objects of different charges are together. The end would be more charge will cause its electrons to flow to one that's more positive. The device I've got here is what we call an electroscope. It's a metal ball with metal stab attached to two gold-plated leads. This is basically a conducting system so that the electrons can flow freely without any resistance. And if I touch it and run into it, the leads push out because they're both negative down and they're held from each other because like charges are metal. Okay? So again, what I'm going to do is I'm just going to grab this and allow the electrons to transfer out. And I'm evidently not letting all of them out. Letting most of them out. Good enough. Picking up all electrons from the rabbit for the frictional contact.
Did that shock you?
I know, little. Nothing compared to what was related. Charge transfer. Next up is contact. So when two objects of different charges touch each other, the one with more negative transfers electrons to the more positive. The more negative gives electrons to the positive. To the more positive. Mm-hmm.
So if that's positive and then you're positive, is that why?
I'm not positive. I'm neutral. Okay, I'm neutral. I'm not insulated from the ground, and I'm allowed to transfer electrons from the ground freely. So when I touch the top here, I'm getting some of its electrons. It's negative. I'm neutral, so I'm more positive, but I'm not actually positive. Okay, so I pick up the electrons from it because I am more positive, though still neutral, and they distribute between and the ground.
So if something's touching the ground and it touches something that is not on the ground, then it'll neutralize it?
Yes. Good with that? Okay. The last method of charge transfer, induction. Now, this is a little trickier, but again, the electrons on the plastic. This time, rather than contacting the sphere, I'm going to touch the sphere here, so it's grounded at the moment, meaning that it's neutral, right? I'm going to bring the rod nearby. Now, what do you think all the electrons were the steel sphere and the electroscope have done? Gone to me. They can't just be there, but they've gone into me and the ground. So if I take away my hand now, this is going to get back in. And if I remove this becomes charged through induction. Now I want you to watch. It's deflecting everything when I bring the rod nearby. What it's doing is it's causing motion of the charges within the object. Okay? So it's, oops. No. So I'm going to give it one more try here. So what we're doing for charging by induction, we're creating a charge by pushing the electrons within the object or out of the object, actually ever touching it. Well, that is with the charged object. Again, I'm going to give it a pass out, bring in the electrons, remove my hand, remove the rod, and they're not very effective, but you can see that they bow out just that way. Last one we said was induction.
The balloon thing, it's not actually positive and the balloon is negative. The balloon is negative and you are neutral.
So, yes, until the balloon has start, you're both neutral. When you rub on your hair, the balloon takes the electrons away from your hair, and your hair becomes positive, and the balloon becomes negative. Okay. All right. So this is creation of a charge. The creation of a charge by pushing electrons around within an object or off of an object. By pushing electrons around, on, or out an object without contact. Hmm? All right. So what this is a Van de Graaff generator. First of all, is plugged into the wall, so I've got a constant supply of electrons. But it uses these types of charge transfer in order to a whole bunch of charge at one location. So in the bottom here, there is a brush that the rubber belt runs past when this thing is turned on. How or through what method of charge transfer does the belt pick charge? Friction, or the triboelectric effect. Okay? So either through friction or the triboelectric effect, same idea. The rubber belt runs the electrons up to the top, where they can jump to the gold foil. That gold foil then is in contact with this, and the electrons are transferred to this dome. Contact. So it's contact. Okay? Now, before we turn it on, we've got to go back a step. The question. So, today's daily question asks, why are you safe when you are inside a car if the car is hit by lightning? So let's take a look and see what you guys are saying. The half of you that answered, actually no, let's do it this way. Ashley, what do you think? Why would you be safe inside the car? What about it? Okay. Esteo, what do you think? If electricity, what do you mean by go over you? Ethan, what do you think?
Okay, I don't know exactly what it is, Mark. My science teacher said something about him being at the lake on the boat, and as he was like coming back, there was like a rainstorm and his boat and made his car stop. But like, I don't know if it keeps him safe or if it just like turns off the car.
Okay, so you're saying that somehow the car just gets shut off instead of being, okay. All right. Taylor's not here. Josie, what do you think? You're just safe, okay? Kiara, do you want to help her out? Logan, I'm coming back to you next.
Sure. Does the material deflect the electrons?
What material? Logan, what do you think? You're right. As long as you don't touch the frame, you're safe. Zane, you look like you want to pipe in. Okay.
It neutralizes it like the balloon.
Taya, what do you think? Maybe you didn't hit submit. What'd you say?
I just thought that like the not being in the outdoors, like and being in something like protected more.
Okay. Asia's not here. McKenna's not here. Matt, what do you think? What'd she say? That doesn't sound like a good steal of an answer. Amara, what do you think? Okay. Energy goes into the car. Jack, what do you think? Rubber from the tires. All right, so when I ask this question, the most common answer, not just for students, but for the public as a whole, is that they think that they're safe from the lightning because the rubber tires are insulated. And electricity can't travel through the tires very well. However, I want to pose to you that air is also a good insulator. And the lightning bolt has just traveled through miles of air, and it hasn't stopped. And it's going to be stopped by like 2 inches of rubber? I don't think so. Okay? So the reason that you're safe inside a car, it has to do more so with how electrons interact with each other than anything to do with the car itself. So if I draw a car here, because it's a conductor. And so if I'm going to strike this car with a lightning bolt, I'm just going to place an electron here. If the first electron from the lightning bolt is here, where's the next one going to be? Why? So, like charges repel. So Brooklyn's right about where it's going to be, and Jensen's got the explanation. So the next charge is going to be here. Where should my third one be? Okay, kind of in the middle. And now where? Okay, and I'm just going to keep filling these in. Why am I only filling them in on the edges? What if I tried to put one here? What would it feel? What would happen? Well, just based on the stuff that you guys have already worked with today, and let's say a second grader's understanding of how charge works, they go away from each other. So if I put an electron here, all of these other electrons are pushing on it, and it has to push to the edge. So electrons travel on the outside of conductors, such as cars, because when you have multiple of that charge, they're pushing each other away. And the furthest they can get away from each other is the edge of the vehicle. So when we run our Van de Graaff generator, and we have electrons running to the top here, the dome of this, nothing exciting goes on inside, because this is a conductor. So all of the electrons go to the outside of the conductor. And when I turn this on, you can hear those electrons reaching the edge of the Van de Graaff generator. And really what you hear is them ionizing the air. They're actually making ozone right now. So when all those electrons are grouped up together there, they've got a large force on each other. And as soon as one's got to tap out, it'll take it. Sure. What?
You're like 6 foot. I'm like 5 foot.
So what there is a volts and path out of the Van de Graaff generator because they're all exerting forces on each other, pushing each other away. Now, first of all, next one I've got for you is a series of tin pans. I'm going to put the tin pans on. When I turn the Van de Graaff generator on, what's going to happen? Okay, now let me clarify this. Are they all going to come flying off at once? Is it going to be one at a time? Or are they just going to kind of levitate up over top of it as a group? So, I'm waiting for it to be quiet so I can give you an answer. Why do you think it is which one you do? Somebody got a reason for their guess. Or should I say, have an actual hypothesis?
Yeah.
So, okay, the electrons are going to the outside. So which one do you think is going to happen? All at once or one at a time or levitate as a group? One at a time? Okay. Eva. Okay. Here?
I think they're gonna go like above it because of the reason you just said because the electrons are on the outside, so it's like kind of neutralized.
Okay. Anybody else? Alright. So
Now explain that to me.
Ashlyn already did. She said that when the electrons are gathering here, they're going to start gathering on the outside first. When they gather on the outside, all the electrons are on the dome and the top pan. There aren't really any electrons on the next one until this top pan's blown off. Then the electrons can start gathering on the next one. And then they can start gathering on the last one. Because they only gather on the outside edge. And when they're stacked, this is the outside edge, not these two. Yeah.
So why does it only go onto the top one? Why doesn't it go on the outside of the lower layers?
Well, for the same reason that it's going to be safe in the car. Those other electrons on the set are going to force them to go further. They can't stay into those middle layers because they're feeling a larger force from the other electrons, pushing them to go even further out. Now for this next part, thank you to volunteer. Yeah. You do, but step up onto the platform. Make sure you center it. So you kind of want to twist a little bit side. Yeah, there you go. Perfect. Shake your head just a little. So what you can see the circle here. And what's happening is Kaya's hair is acting just like the fans, just like we described for a car. The electrons that she's getting from the Van de Graaff generator are transferring out over her, and the furthest they can get away from each other are the extremities of her hair. And because each strand of hair is now having the excess of electrons, they're pushing apart from each other, and she can start to see them coming up in front of your head. Shake your head a little bit more. Good. Give it a shake. There you go. So she's got more and more coming up. Who else could be good? Well, maybe. Maggie's could be really good. Brooklyn's might be really good too. So I'm looking for someone whose hair is thin, not incredibly long, and is like dry looking. Okay, you put your hands up. I don't mean dry, I mean like not loose. Who else wants to give it a try? This is going to be boring. And Max is already doing something exciting. Really, I just cut my hair a few weeks ago.
I don't know how you do that, but why do you stand on your body?
So you're standing on the foam to insulate yourself from the ground. If you aren't insulated from the ground, the electrons just flow right through you and they don't collect up. Go ahead and put your hand on the dome. I can see him starting to move. Ooh. You just start to the floor. Yeah, you want to step a little bit more sideways so that you're centered. Yep. A little more. There you go. And shake your head just a little bit. Good. So shaking your head just a little bit allows them to like detach from each other and start spreading out. Give another try. This is doing pretty good. Katie Freeman's, like as soon as she touched it, it was pretty impressive. This is actually really good. Yeah. Yours is actually doing really good. So you can see some of the individual ones out there pretty far. So Eva, I want you to try something. Take your hand out here and make a fist. And then open it. Just a little bit. And close it again. So if you watch like some of these strands, some of her strands of hair will actually go down and up as she opens and closes her fist. Just a little bit. Yeah.
Oh yeah.
So what she's doing is, as she opens her hand, the electrons from her hair are rushing up there because there's more space. Then she closes it, and they're rushing back up to her hair. All right, you can go ahead and take your hand off the dome. All right, who else wants to try? Go ahead, Jensen, Jan. No. So, for those of you who have gotten up there, did you feel your clothes like stuck to your body? No. How about now?
No.
All right.
Will it shock me again?
Yeah.
I don't want to do that.
Here, I'll turn it off for you. Sleep, not sleep. Sure, good sex.
Don't turn it
Ooh, what's your own clothes?
on. I'm really funny.
No, yours is really good. Hey guys, I want you to be quiet for just a second. Move your hand around. She's got lightning arcing off of her fingers.
Wow. Someone come touch me. Come here. Ow! Why did you do that?
I told you to. So this is about as close as you're going to get to force lightning as possible.
Okay.
Just the extra electrons. Pull your hand off. No, this hand.
No, I think it shocked me.
Not if you don't take your hand off. Actually, what? Let me leave this on. So, show you that it is just a transfer of electrons. I'm going to fluorescent a light bulb. I want you to watch the light bulb closely.
Oh, are you like to watch that?
Alright, so what's going on is the electrons are jumping through the tube, lighting it up, and actually I'm getting a spot right here that's just kind of going like this. So the same signals that would normally cause my hand to close are being sent by the Van de Graaff generator, and my hand is closing. Let's see here. What else do we do?
What does it feel like? Like inside?
Did it feel like it did when I touched it? Marty, what if I put my phone
Why can't I do it? Well, you've been doing this all day. You can be all like, yeah, I got it.
I think this is the best one. I almost earlier I got lightning to actually jump through my fingers.
Yes. Are you able to like see it?
Only very, very rarely.
I'm like,
That was a good one. Wow.
that was,
That's exactly what we did. No, I don't want you to finish it. Yeah. Let me just see here. Do I still have them out? No, I put them away. There we go. I just needed to find something set. There you go. For the telescope purpose, use a flashlight. You actually create the telescope. Yeah, okay. What's this question? Step number 5. Okay. Excellent.
I just have to finish like a couple questions. That is
Okay, sounds good. Bye.